At the International Conference on Open and Innovative Education hosted by the Open University of Hong Kong, Professor Roger Azevedo from the Department of Learning Sciences and Educational Research at the University of Central Florida speaks on the topic of measuring self-regulatory processes during learning with advanced learning technologies. Professor Azevedo shares some of his research on using different advanced technologies such as intelligent tutoring systems, multimedia, and virtual reality to examine and monitor the cognitive, metacognitive, affective, and motivational self-regulatory processes during learning.
So before I begin my talk, I like to do the usual, which is, start off by saying that this kind of work is extremely expensive to do. This kind of work is extremely interdisciplinary in nature, involves a lot of folks, so colleagues in computer science, different areas of engineering, medicine, STEM ed, K-12, etc. So you'll see some of the examples of that. And I really want to do is kind of show you what we've been doing not only for the last 20 years in terms of analyzing self-regulated learning, which really means we're interested in how humans monitor and regulate their cognition, their affect, their metacognition, and motivation anytime they're asked to learn something or to perform a task. So you'll see some examples of that. I want to show you also the kinds of examples and work that we do across domains and also across the world, because we have partners all over the US, Canada, Australia, and in several countries throughout Europe. So let's start off with kind of an overview of how we approach this task. A lot of the research that you see that's published in certain areas basically looks at learning and technology, but they tend to use pre-test and post-test. And as a psychologist, that's wonderful. The problem is I have no idea what you did as a human between pre-test and post-test. Okay, so I am in the business, and my colleagues and collaborators, of understanding what those processes are. So I want to kind of take you a voyage in that. So we start off with theories and models of self-regulated learning that draws from educational psychology, cognitive psychology, educational research, etc. Then to context. Usually we have a human and a machine operating in a particular context. It can be a factory, it can be a classroom, it could also be a research laboratory, okay, or an operating room, or a cancer center. And really what I'm going to focus on today is this third part, is the measurement. We measure both self-regulation before and after, but today I really want to focus is the during. In other words, what is that human doing, okay, or humans doing when they're interacting and learning something. For the analysis of multimodal data, basically I am not going to inundate you with tons of research findings. We have tons of those. If you're interested in the actual findings, I'd be happy to share them with you. And then once we analyze that data, so for example, the cognitive processes, the metacognitive monitoring, the affective reactions that students sometimes have, and their motivational processes, and perhaps social processes depending on the context, the question is how can we make a model to make that machine or the intelligent tutoring system, the hypermedia environment, the serious game, the virtual reality more intelligent, okay? And we can go into a very long discussion of what it means for a system to be intelligent. And that helps us refine some of the theories and models. So that's kind of an overview. In terms of how we approach this is that, as I mentioned, we examine cognitive, affective, metacognitive, and motivational processes. You're going to see that acronym used quite a bit, called CAM, both in school settings, so K-12 STEM, but also in professional settings. So we work with physicians, we work with nurses, we work with teachers, okay? We work with biomedical engineers, etc. And we're looking at what is the effectiveness of those processes in terms of enhancing their learning, their performance, reasoning, etc. I was trained as a cognitive psychologist. We do both applied research, so there will be experiments where we actually try to induce negative emotions in students to see how they regulate. But then we'll also spend tons of time in the classroom with teachers, trying to understand how a teacher teaches STEM. What are the issues? What are the feedback mechanisms? What are the types of scaffolding? So we go all the way from one extreme to the next. We also converge different types of data. We're not satisfied with just looking at pre-test and post-test. That is not enough to understand learning. So what we do is collect lots of multimodal data. We also collect self-report measures, okay? And yesterday we talked a little bit about the criticisms of solely relying on self-report measures. Self-report measures measure students' self-perceptions of who they think they are. I'm not really interested in who you think you are, even though that's important. More interested in what you actually do. Okay, so that's going to be a very subtle difference that we have. And so this is where you see emerging research that's been published in all kinds of journals, including the International Journal of AI in Education, Computers and Human Behavior, Journal of Educational Psychology, etc., on the emergence of multimodal, multi-channel data. And then we also look at, very specifically, what is the temporal unfolding of those self-regulatory processes, but other, because it could be that there's an external regulator. There's a teacher regulating me. There's a parent regulating me. There's a nurse trying to make me understand why it's necessary for me to have this particular treatment. So multiple modals, and then of course all of this to design learning environments. So I just want to give you a sample of some of the systems that we've developed with our collaborators. The top one has been funded for over 10 years. It's MetaTutor. It's an intelligent tutoring system that is designed to train students on how to regulate their learning. We also work with colleagues at North Carolina State University. The next one you see is Crystal Island. Completely different. That's a serious game. Your job is you land on an island and you're learning about scientific reasoning, problem solving, and microbiology. And your job is to actually solve the problem, okay? We also work with teachers. So we got some funding to do virtual reality. Here's an example of a student, a 9th grade student, okay, back in Raleigh, where we basically worked with a teacher. The teacher brought us her hand copy of her photosynthesis unit, 3-week unit, and we took that and we, in collaboration with an industry partner, we turned it into a photosynthesis exercise, and we collected some data because part of the big problem or issue that we're dealing with is, are these new technologies actually fostering learning, and can they be used to also enhance student self-regulated learning, and what would that look like? The bottom corner is tangible computing with our geospatial colleagues, and there it's completely different. They're not using a computer, they're not using a screen, they're not using a tablet. That looks like basically a table, and it's got kinetic sand that has kinetic properties, and what you're seeing is that you're projecting a computational model of the weather, and the students are engaging in collaborative problem solving, using their hands to make barriers to stop the inundation of a coastal system. And so the idea is, as you are manipulating by using your hands through embodied cognition, okay, you're getting near real-time feedback on whether you're actually inundating both people's houses and actually potentially drowning them and destroying property. Okay? So the question again is, are those types of techniques, technologies useful for learning, and also what are the self-regulatory processes they're using? Now, this is going to sound a little, I'll use the word crazy because we're amongst friends. Okay? So what we wanted to do is, we had firefighters that basically wanted to use this kind of equipment to train firefighters. So I challenged the computer scientists and the geospatial scientists in that, how about, instead of having these two people who are instrumented because they're wearing an EEG, and he's wearing an eye tracker, and they're both wearing an electrodermal activity bracelet, because we want to see the physiological arousal as this temporal simulation is going on. What about if we took these two people, the humans, and we minimized them into like Ant-Man and the Wasp, and inserted them into the landscape? So apparently as of today, medically and biologically, we can't do that. We can't vaporize humans, okay? But the solution is that, guess what? I can actually not only have a tangible computing, but I can use a laser pointer such as this one, and I can point to anywhere on the landscape. And guess what? Using virtual reality, I could actually see what it's like to be right there. So now we ask questions, can this student actually transverse the forest? Can I have data visualizations showing photosynthesis? Can I have a haptic glove that I can actually go up to the tree and feel what birch may feel different than maple? And if we wanted to involve non-STEM fields, well, what did this look like 50 years ago? Or dare we ask, what is it going to look like 50 years from now? And you can actually bring history and other potentially art components in here. And then we also work with physicians where we're actually in the College of Medicine trying to figure out if augmented reality and virtual reality is effective for not only undergraduates, but also graduate students, residents. So lots of technology. The problem is the technology keeps being produced faster than we can come up with data that actually proves that it is worthwhile and actually impacts learning, etc. Okay? We also have some other data. I'm not going to get into this, but this is team performance, where we look at high-fidelity mannequins. These are near end-of-life scenarios, where now it's looking at team performance. Basically, this patient will die if you do not treat her in the next 10 minutes. She's got pulmonary embolism and she is pregnant, so you have to save both the mom and the baby. And we push the medical students and the residents to the brink where we actually disrupt their ability to engage in diagnostic reasoning so that they also learn how to deal with when somebody dies, and how do you deal with patient and their families. Okay? So the question here is looking at the emotion and the emotions of the team leader, and how the team leader basically monitors and regulates the emotions of the entire team, okay? And then how do you deal with that, with the fact that you have to tell bad news to the family members, okay? Some other work. Now, the focus by the National Science Foundation has been on workforce performance and preparation. Apparently, we're obviously going to have a shortage of skilled laborers, etc. Top left is a project that we submitted that looks like it's going to get funded by the National Science Foundation, and this is to help skilled laborers who basically put up drywall, but they put up drywall in historic buildings. So they need to understand what they can and cannot do to these buildings. So it's basically construction. And the idea is to use augmented reality to supplement not only the historical plans and blueprints, but also to facilitate their understanding of what they can and cannot do. So this involves engineering, computer science colleagues, and also historians, which is interesting because we've never worked with historians. And then some other ones, like biomedical engineering, where we're actually feeding emotions and emotion regulation into the prosthetics and the machine learning that actually moves the upper or lower limb. So many, many applications, including construction workers, okay, with work with engineers in construction environmental science. Apparently, every 6 minutes, somewhere on our planet, a construction worker dies because they're careless, they don't have the right training, etc. So this example here is an example where we take photographs of actual construction sites that have subtle and not so subtle hazards. And the idea is we actually get to look at the eye tracking to see the detection of these construction workers. Can they detect where those are? And then we use their gaze behavior, in this case you're seeing a heat map, to actually come up with an individualized training to ensure that they basically don't cause any harm to themselves or to others. So a lot of applications. So the question again is, what can we do with these technologies? Are they actually enhancing learning? And again, well, we need to collect multimodal data, not just eye tracking or self-report data. Well, how do we collect this data? This is our typical laboratory setup where somebody's instrumented. Okay, we collect tons of data. The only thing that you don't see in that bubble is them verbalizing. Okay, but we could include that. The most expensive piece here, well, the most important piece, of course, is the human. Let's not forget the human, right? The second most important piece is the eye tracker, which is very expensive. All right, so it can be up to $40,000, if not higher. All right, so there's issues of scaling up that we are trying to deal with. Okay, in terms of using other eye trackers if you're in a classroom or in the real world context. And here's another one in terms of, for example, when we pull students out and they're doing the photosynthesis, this is the kinds of data that we can collect, including physiological data, everything she's doing, including an output of what she's actually solving. So what we're seeing out here is what she's actually seeing and doing is being outputted so that we, as researchers, can get an attempt to understand what is she doing in terms of strategy use, metacognitive processes, potentially, but more importantly, also have the teacher tell us what he or she thinks the student is doing, okay? So then potentially we can then feedback and augment what the student is potentially doing in terms of learning. In terms of theory, right, as a psychologist, we always use a theory. This is one of the dominant theories that we use, which is Phil Winnie and Alison Hadwin. They're both in the University of Victoria. And we use this because it treats self-regulation as a process, right? Anytime you see a model that's got, arrows, double-headed, single-headed arrows, there's a flow of information. And I'm not going to get into the details because we can spend 3 hours just talking about this model, but it's an important model, and the work that we do has a theoretical basis, right? And we try to understand is monitoring and control. We're monitoring what we're doing or what others are doing for us or with us, right? And then the question is, how are we regulating, which is the control part. It also assumes that when students are able to regulate or not able to regulate, is that the reason you're doing either one of those things is that we have internal standards, okay? So if I'm reading, I'm a kid and I'm reading, how do I know I'm actually understanding? Well, that's assuming that you are monitoring what you're doing, right? So if I don't understand something, the question then becomes, what do you do about that? Well, an adaptive strategy would be to go back and reread. Well, what about a student who doesn't understand, and we have indicators that they don't understand, and they keep reading? Why is that student rereading? They just clearly indicated, right? So one of the things that we never have access to as researchers, as parents, as faculty, is the access to these internal standards. How do we get access to the human's internal standards which allow him or her to actually regulate and monitor, accurately monitor their learning? Okay, so that's an area that we should do a lot more work in. And then, of course, we converge this model with other models of affect, models of motivation, and more specific models that come from cognitive psychology, mainly, of metacognition. So here's an example of Phil Winnie's model. If you actually look at the model, this is showing this as a linear progression. By no means should be taken as a linear progression. Okay, according to him, he's got two very important points, is that we come to a situation with conditions, we apply some operations, and that's a fancy name for strategies. And here's the list of potential strategies: searching, monitoring, assembling, rehearsing, and translating. And then what I've done is populated that with some of the 35 plus processes that we have actually been able to collect with over 700 students over a period of about 10 years using concurrent think aloud protocols. All right. So if you use a strategy, you come up with a product, the product then you evaluate, and then you have some internal standards. Okay, so what is missing here, and I highlight in red so that you don't think it is a very simple model. It is simple, but what you're not seeing there are the feedback loops that go not only across this line and this line, but also between both of those arrows. And that's where we capture the process data using multimodal data with different techniques. Another way of organizing this, when somebody comes and asks, well, I'm interested in cognitive strategies and metacognition. Okay, so this was an attempt, if you look at the top, the process, okay, component, and if you wanted to look at cognition, affect, metacognition, motivation, well, here are some tools, like screen recording, converging think aloud protocols, eye tracking, log file data. And so, for example, we know very well that if I'm interested in understanding your cognitive strategy use and your metacognition, okay, then I should be using perhaps concurrent think aloud protocol, because you'll actually get someone, basically they could be reading, oh, I'm reading about the mitral valve, and then somebody will say, oh, I don't understand this. To me, that's beautiful, because now your language has exposed the fact that you are monitoring, and I can segment that, okay, and then I also have valence. You actually indicated that you don't understand that. That's wonderful. Question for me then as a psychologist, how you regulate that. What strategy are you going to be doing to regulate that? Does that make sense? Some of these are question marks, like yellow, all right, because sometimes we, even with concurrent think aloud protocols, students will bleed over. They'll say, like with MetaTutor, when Sam asks them to use a strategy, by the end of the experiment, they'll say, oh, I hate Sam. It's pretty harsh, but it's like, take it easy, kid, okay? Or I'm just not interested in learning about this anymore. Okay, so that's a motivational, all right? So, again, as I said, this is high level, and each of these cells can actually be broken down into the different dimensions, which are actually not represented here. And physiological sensors, each one of these, this is just a list of 5, there are plenty more. Each one of these should have their own row, if you will. And then some other ones, products, self-report measures, etc. So what are the contributions? If we look at the multimodal data that we're collecting with some of these instrumented students, right? So most of the literature that you see collects log file data, and log file data is wonderful, right? I mean, that's been the initial root of when we talked about uni, or just one data channel. That was log file data, a single channel. It's great because it collects these processes anywhere between milliseconds and seconds. Sometimes you can get to minutes. Hours is a little more hard to make inferences just based on solely on log file data. And it tells us about the sequence, but what about the dynamics? That's not captured in log file data. So how do we recreate dynamics from the log file data? We get a lot of data. We can talk about the sequences, the frequency of use of these strategies, the duration. Those are all critical, and they actually have served what we know about this. And then if you look at the Journal of Educational Data Mining and the Journal of Learning Analytics, you'll see a lot of data where a lot of our colleagues across different disciplines are using these types of data, both frequency, duration, sequence data, to look at sequence mining, right? So if I know that you are showing frustration, because that's what your face is showing, you are not a very good metacognitive monitor, and you keep using the same strategy and not very effectively. Can I take those 3 dyads, or triads I should say, and is that predictive of what you're going to do next, or how much you're going to be learning, let's say, today, or next week, or after the academic year? So we keep asking these questions about what is the right, is it one? Is it a dyad? Is it a triad? We've also attempted to work with quintuplets. So the question is, what is the predictive nature of those sequences? Now the challenges that we and others in our area are focusing are things of theoretical assumption. How do we take, for example, Winnie's model or any other model and apply that to the multimodal data that we collect, right? I'm not going to go through all these points, but one thing to keep in mind is the models that we have of cognition, of instruction, of learning tend to be so abstract, so high level and descriptive, but they're not descriptive at the right point in time where we can then also drive prescriptions. Because what do you do for a student, okay, if you're collecting multimodal data? So I can tell from your eyes, for example, that first of all, you're not focusing on the right content, instructional content. I can tell from your face that you keep getting frustrated and confused. You are a really poor metacognitive monitor, okay, and you don't have the strategies. This kid is in a lot of trouble. So the question is, instructionally, tell me which model of instruction would actually indicate to us what should we do for the student, right? How do you intervene? What do we take care of first? Do we take care of your motivation, your emotions, your cognition, your metacognition? When do we do it? How do we do it? And who's going to do it? And then the big question is, how do we know that your intervention or our intervention was effective? One of the big problems I'm going to focus on is this equidistance. So yes, log files could be at milliseconds, but then how do we converge these processes that have different durations? Or processes that I'm using an eye tracker that samples at 250 hertz. Meanwhile, I'm using an electrodermal activity bracelet that samples at 30 hertz. How do I temporally align those data? Because now I'm getting different amounts of data for each time unit. And are they all relevant, all right, for making inferences about self-regulation? How do we handle these issues? The other big issue is the qualitative nature. All the work that we've been doing and that we see in the literature is focusing on quantitative measures, quantitative analyses. Well, what about the qualitative analysis in self-regulation, in metacognition? When does a student show that they have developed an emotion regulation strategy and now they're efficacious about using that particular strategy to handle a complex physics problem? What does that look like? Okay. The other challenges is we tend to build environments for a particular set of students of a particular age group for a particular task for a particular topic or domain. And that's great. But that's what we see in the literature. So like MetaTutor, well, yeah, we make assumptions about mental models. We make assumptions that you have low prior knowledge because we don't use medical students, or we haven't done that yet. Okay, they're non-biology majors. And they're using hypermedia. But what about the contextual variables and conditions and theories? Well, we have choices. Which theory of self-regulation do I use? Well, I showed you that we have a tendency to use Winnie's information processing model. But why not use Zimmerman and Bandura's work on social cognitive theory? Why not use that one? Or SSRL. So if you look at the work done by several of our European colleagues, like Sana Yarvala, who's at University of Oulu, and Alison Hadwan, University of Victoria in British Columbia, Canada, well, there's a lot of work on SSRL now, and ERL, or external regulated learning, or social self-regulated learning, or CORL. So which one do we use? Because in our case, most of the time, it's not just about a human using a machine, but it's a human using a machine. The machine usually has some kind of embedded agent. It's a pedagogical agent or an intelligent virtual human. So we're simulating that as a social interaction, okay? And then if that's not enough, okay, and that's just for cognition. Well, but then we also look at emotions. But guess what? Well, look at emotions. This is just a sample of the different emotion models and theories that exist. So do I use Pekrin's control value theory? Do I use affective dynamics from de Mello and Gracer? Do I use the EASY model from our colleagues in the University of Amsterdam? Okay, the Van Cleef model. Do I use emotion regulation from James Gross? And then the question is, even more challenging for us is, how do we combine two models that were never meant to be combined, have different assumptions about cognition, metacognition, and emotions? All right, because we need a theoretical model to look at self-regulated learning. All right, so there's lots of challenges. And then, of course, to top it off, we usually adopt some kind of theory or model of instruction. Right? So some people talk about Vygotsky and others talk about Piaget, and we'll talk about mental models. So can you imagine the difficulty in putting all this together? But we have some solutions. So what we want to show you is a snippet of some of the data. So when we're looking at cognitive processes or strategies that students use to control, here are some examples. And this by no means is an exhaustive list. So we can look at note-taking. We know with MetaTutor when a student basically, because we give them the ability to copy and paste into their notebook, But here's another example. All right, we allow the student to copy and paste. We know your low prior knowledge. We're tracking you. We have the multimodal data. But at what point would you as a teacher or an instructor tell the student to switch from copying information, which is low-level processing, to engaging in more deep understanding or processing? Let's say paraphrase. We don't know that. Do we know, if you know of any theory that actually stipulates when we should do that for a particular student, then that would be great, because guess what? We're trying to design systems that will do that. But if the humans don't know how to do that, our theories don't know how to do that, well, we rely back on our experts, human experts and teachers to help us with those, okay? We obviously look at log file data. That's kind of our bread and butter. We can actually make inferences. This is actually a screenshot from an eye tracker, a portable eye tracker. So we are starting to make some inferences about cognitive strategies that could be used based on somewhat robust signatures of eye tracking. And also in terms of how you read and then basically how you fill out things like the concept matrix in Crystal Island. Again, this is just a subset of examples. Affect. That's been our biggest albatross, I guess would be the best word to describe it. Okay? Because it's complex, it's sensitive, it's sometimes inaccurate, and it requires a lot of not only processing, but post-processing. And then if we have to wait so long for the physiological data to be analyzed, imagine the time lag, right? Because now you're going to make an intervention based on the physiological data, and it may be seconds or minutes. You may miss an opportunity to use that data to actually intervene in terms of scaffolding a student or providing feedback. So this is still a lot of work in progress in terms of what do we do with the physiological data. So we have it. Our biggest one has been facial expression. So this is a student who kind of looks confused. This is the A4 action unit, which is the furrowed eyebrows. So we basically, it's looking at a constellation of muscles in the face, okay, that are indicative of particular affective states. We tend to focus more on the learner-centered affective states. So we're talking about confusion, frustration, boredom, and then neutral, okay? Even though, okay, and most people kind of ignore the basic emotions. However, when we are designing environments, advanced learning technologies for example, cancer patients, right, and the content is biomedical knowledge about what cancer is, and you've just been given the diagnosis, all right, I'm not going to be seeing a lot of confusion or frustration. I'm going to be seeing a lot of anger, okay? So part of that is, can we then embed pedagogical agents to facilitate and help the patient downregulate her emotions so she can allocate her resources to understanding, for example, what a lymph node is or what an infiltrating ductal carcinoma is, okay, and how that spreads. And then we've been experimenting with taking the same data, the facet data that comes out of this software, and actually creating a heat map of the intensity of those emotions. And one question, which I'll show you in a couple of slides, is can we then feed this back to the learner to help him or her monitor and regulate their emotions? Okay, and that's kind of an open question that exists. Metacognitive processes, so this is, we've also been experimenting with showing the student back, they're learning about science topic, they have text and diagram, and they have an agent who actually expresses either neutral, which is very creepy, versus confused, like, why are you spending time on that text, it's irrelevant, or joy, oh, I see that you're spending time on that diagram, and it is relevant, so kind of you're on the right track. So we're trying to basically create these heat maps based on the student's eye tracking, so that we can then basically confront the student, here's your data. So instead of me telling you, look, you didn't do very well in answering the science question, well, here's the reason why. I can tell you that you didn't look at the agent, but I can actually now show you, there's your data. It actually shows that you did not fixate long enough on it. Instead, you fixated and paid attention to this first paragraph, which we actually included in there, but it was irrelevant, okay? So can that help a student calibrate their metacognition and understand? Here's kind of an abstract representation. If we're taking all the multimodal data and we think about how we divide it between cognition, metacognition, affect, and motivation, the bars basically indicate each of those multimodal data channels. And then the y-axis is the hypothetical amount of inference that you would have to make if you just stuck to that one data channel. If you also see is below the line. So if you look at motivation, it's the only one that's different from the other three, right? Because for motivation, we keep using self-report measures. And so the question is, when are we going to switch? Can we have trace data of students' motivational states? So if we look at the theories, we think about interest, self-efficacy, task value, intrinsic motivation. How do you use multimodal data to track, for example, any of those motivational processes without using self-report measures? Okay? And of course, this is oversimplified again because unfortunately, you know, as humans, as researchers, we're stuck with these two-dimensional, I mean, I can make that three-dimensional, but that should be actually nth-dimensional because there's so many different components, right, in terms of how much eye tracking do I have to sample, and can I, above the line here, to make an inference about an affective state. Can I? All right? Versus facial expressions. That gives me the data that I need to make an inference and requires less inference than if I potentially could use, maybe not, eye tracking, or even can we detect affective states, for example, from electrodermal activity. And the distance, of course, again, those are all, we can spend, you know, hours talking about that, all right? But it's some way of actually coming up with a way of summarizing what we can and cannot do and the level of inferences that we make. Here's an example of some of the metacognitive processes, okay? So they tend to be quite robust. I selected these 4 because these tend to be 4 that are not only used with hypermedia or ITS systems using learning about biological systems, but these can be used if you're reading history. Okay, so like feelings of knowing, judgments of learning, and you'll also see this throughout the literature. Okay, it doesn't really matter, you can be doing math. All right, so this gets to an issue of how domain dependent and how domain independent are they. And we go back to Winnie's model in terms of looking at the cognitive conditions and the task conditions, et cetera, that relate to that, and the description. So one of the things that we would love to do, and one of the reasons why we stopped doing think alouds, is because it's too time consuming and laborious. But the idea is, now imagine that, you know, the student is giving the think aloud, and in real time, okay, we can actually analyze, because we know when we have the coding schemes, we have tons of examples, frozen expressions, et cetera, and be able to categorize those in real time, as opposed to doing it post hoc and then changing the system after it's post hoc. So some other examples. So here's an example of, if you just looked at one data channel, all right? So this is in Crystal Island. This is actual data from a college student, a non-biology major. And all we've done is turn on the eye tracker, right? So this is what you see, what we would see as researchers. But we ask the question, if we do the same, okay, when the student is actually trying to solve this microbiology problem with Crystal Island, would providing the student with their own eye tracking, would that increase their metacognitive awareness? Okay? Or for which students might that occur? Because for some, it might actually induce extraneous cognitive load. So just questions that we have. So the question here is, let's not hog up the data that we collect, this multimodal data. We have to provide that back, but in what forms do we provide that back for the learner, for the teacher, for the trainer? So you actually get to see what they're doing. If you didn't have screen recording, you'd have no idea what they're doing. And if you have no multimodal data, you're just doing pre-test, post-test, you can hypothesize until the cows come home about what they were doing. You have no idea what they were doing, okay? And that's part of the issue. Here's another one. So I went from one data channel, okay? This is a student using MetaTutor. So here, I'm trying to show you the full Monty. You get to see his face. Now, this one's been annotated for today's presentation. You get to hear the agents will pop in and out. You get to see his eye tracking. Okay, he's starting off there. So the bigger the red circle gets, the longer the fixation. Okay, and you'll actually see his behavior because you're going to be screen recording.
Let's set up some sub-goals.
Okay, so how about we learn about what are the effects of smoking? So I would like
so you're setting up a sub-goal?
About the effects of smoking on the lungs.
Very good. Let's try to set a sub-goal that covers lungs. How about we try to learn about path of blood flow?
Okay.
Wonderful. We've just set up a good sub-goal.
So, so our sub-goal is path of blood flow.
So we don't tell him what he reads. He's got to select what he reads. That's part of regulating and learning.
We learn about the immune system. So other aspects of the circulatory system, immune system. The immune system is a group of cells, molecules, and organs that are coordinate to defend the body organs and pathogens. Let's take the notes. The immune system is a group of cells comma, molecules and
So I'm gonna
organs.
stop the
that
video right there.
Coordinate.
So you get a better idea of what this multimodal data can be? And again, this is the convergence that we, again, as researchers have access to. Imagine the power of giving this to a learner, right? You spend about 2-3 hours learning about the human circulatory system, okay? This is your data, okay? You didn't do very well on the quiz or on the test, etc., okay? Now let's go back and review what exactly you were doing, okay? As opposed to like, oh, I get a score and all right, well, how do I change my behavior or my studying habits, okay? Or imagine the power of this for an instructor, whether you're a faculty member or K-12 or a trainer, it doesn't really matter, okay? A physician, etc., a nurse, all right? What is the power of actually showing the multimodal data when you are now revealing your processes to us, okay? So here's another grant that it's been what, a little over a year now, so teacher dashboards, and this is all in the spirit of taking the data and showing the data. So in this case is, all right, well, here's a typical classroom. What I like to call the dumb whiteboard. It just sits there. Sometimes they use it, sometimes they don't. So the question is, what about if the students were using Metatutor, or it can be one of the CTAT tutors, or any of the systems that you're using in your own profession, right? So we keep using the multimodal data to make the system adaptive and provide individualized instruction for each of these learners. Question becomes, let's not hog up that data again, and let's work with teachers, because we're going to figure out is what data, if you had access to your students' cognitive, affective, motivational, and metacognitive data, how would you want that represented in the teacher dashboard? Which data is most important to you? Why? How do you want to represent it? Okay, and then when do you want to represent it? And then the most important part, okay, part of this grant is that eventually in year 3 is now we're going to instrument you in the classroom, the teacher. So EEG, portable eye tracker, and EDA, and collective verbalization is when we show you data, are you actually looking at the data? How do you analyze that data of your students that you said you wanted? And then how do you interpret that? And then how do you feed that back in terms of your instructional decision making? And is it effective? Okay, so that's a 3-year project, and that's with colleagues, Min Cheese in computer science at NC State, and then we have Sunyi Park, who's also a colleague in STEM at NC State. So this is, now with my move, this was trying to do studies both in North Carolina, my former colleagues, and also in Florida. Because the teacher could ask, I want to see individualized student data. Well, I want to see data on this particular student because she gets frustrated. Or, remember the student? We noticed that she keeps copying information from Metatutor. When are you going to stop that, teacher? All right, because we're giving you that information. Or this student is really off, okay, in terms of the ideal path. So it can be, is it individualized data that you want to see? Or is it aggregate data? This is with other colleagues at University of British Columbia, and also Eunice Jang, who's at University of Toronto, using latent class profiling, right? I don't want to just see individual student data, but it might be the end of the class, right? And now we've collected enough data, I want you to aggregate that data. So using latent class profiling, we figured out that basically with some of this Metatutor data, that we actually have 3 types of students, okay, in terms of their motivation and strategy use, either good or poor, or ones that are doing really well. Or with Christina Conati and her team at University of British Columbia, when we feed them the eye tracking data and the self-report data and other emotions data, can we come up with robust signatures? So here's an example based on machine learning approaches. This is what a student who's disengaged. Well, you can obviously tell this is disengaged, but if we had an eye tracker and we saw that pattern, can we now intervene? Versus the student who's engaged, who's actually looking at the overall learning goal, the sub-goal they set, and they're actually trying to integrate informational forces. Same thing with data visualizations for emotion regulation. So what I wanted to show you is that also leads not only in terms of you giving us data for us as researchers, right? Turning that data back to the learners to empower the learners, turning that data back to the instructors and faculty, parents, etc., to empower them to help their children, learners, etc. But what about the next generation of data scientists and learning scientists, right? Because we keep taking the same traditional stats classes, right? Where all this data basically, we now need a new hybrid type of researcher. It's no longer just good enough to be a psychologist, an engineer. We have to work across disciplines. So how are we going to do that? So how about, here we're trying to simulate is, imagine training the next generation. This guy could be an undergrad engineering student or computer science student or educational researcher or a psychology student. Because now we have the learner, okay? She's fully instrumented. of course, they would be physically separated. And yes, this is very staged. So we're collecting the multimodal data on her. So we get to see her choices, all right, her physiology pretty soon, her mouse clicking, and pretty soon her eye tracking. This is the researcher, undergrad student, grad student, postdoc, faculty member, really anyone. He's also instrumented, because now we're trying to instrument the researcher because we want to know when you are looking at somebody's eye tracking, what inferences are you making about their eye tracking data? Does that make sense? So here, that's what he sees. He's seeing her face. This is all her affect data in terms of the intensity. And of course, this is just for showing, but of course they'll be physically separated because he would also be giving a concurrent think aloud in terms of the interpretation of these data. All right, so thinking about how we train the next generation of data scientists. This is where we're at. The work that we're doing, we're very much into collaborating with many folks. Some of the work we're doing, and I'd like to mention that this is not possible without a huge, I was going to say village, but it's more like a country, I guess, or multiple countries, a lot of colleagues and funding, and I thank you for your attention. Thank you.